This is slide number 32 and I am your presenter Asloob Mudassar. Autocorrelation theorem. So here we in the first line we have defined the Fourier transform of the object at x comma y is equal to capital O at fx comma fy. So this is the Fourier transform of the small object O and is given on the right hand side. The autocorrelation theorem is defined as object O at xy autocorrelated with its with the complex conjugate of O at xy. So you see that here on the left hand side this is actually a definition. So sometimes people replace the O conjugate with O. They write O conjugate simply as O, because this is not important. This is just a symbolic representation. But on the right hand side, which is the integral, that is important. That the in the integral we cannot make any changes except that given. For example, in the integral we have the integrand as O at the coordinate zeta and eta multiplied by the complex conjugate of O at coordinates zeta minus x eta minus y, and the integration is with respect to zeta and eta. Okay, then the statement of autocorrelation. Autocorrelation is represented by the asterisk. So the autocorrelation statement is, let's now take the Fourier transform of this one. The Fourier transform of the above integral, we have used operator on the left hand side with the same quantities and the same operator, that is the Fourier operator, on the right hand side for just before the integral. And we have just written that the output of this integral is equal to absolute mod square of the capital O, which is the Fourier transform, capital O at the coordinates fx comma fy. So the autocorrelation of the two functions will give you the absolute square of the spectrum at the points fx comma fy. So this is actually the energy spectrum. Now let's take the inverse Fourier transform. This is another definition of the autocorrelation theorem. So the first one, so this is the first definition, that is the Fourier transform of the autocorrelation is equal to the absolute square of the spectrum of the object at points fx comma fy. So this is the first definition, and there is another second definition in terms of the inverse Fourier transform, that is the inverse Fourier transform of the autocorrelation between the two spectrums is equal to the mod square of the object function, that is absolute square of O at x comma y. So these are the two definitions of the autocorrelation. One is in terms of the Fourier transform of the input objects of the space variables, and other the inverse Fourier transform of the spectrum of the same object. So you can see that on the right hand side of each integral, each definition, we have the squared quantities. It means that the autocorrelation cannot be negative, it is always positive. Whether we are taking a Fourier transform of the autocorrelation of two functions from the space domain, or we are taking the inverse Fourier transform of the spectrum in the Fourier domain, and both quantities, you see that on the right hand side are the absolute squares. So it means that the both quantities are positive, non-negative quantities. Now you see that in the first integral we have written the absolute square of the spectrum of the object, that is absolute square of capital O at fx comma fy. Now actually we want to establish the result over here. Now let's take the Fourier transform in order to establish the result the same, that is the first integral. We are going to take the Fourier transform of the autocorrelation of the object, that is O at x comma y autocorrelated with the O conjugate at x comma y. So there is a Fourier transform that we have represented over here, but you know that here we have represented the autocorrelation definition in terms of the convolution definition. Look at the convolution definition that we have correlated with the autocorrelation function, and that is the Fourier transform of the object O at coordinates x comma y convolved with the complex conjugate at the coordinates minus x comma minus y. So this is you can see that this is the first line provides you the connection between the autocorrelation function and the Fourier and the convolution between them. So in the convolution we have object O convolved with the autocorrelation of the complex the convolution of the complex conjugate of the object, but at the coordinates minus x comma y minus y. So now this operator, you know that within the curly bracket, this operator is operating on the curly bracket in which we have the two functions convolving with each other. Now this Fourier operator will operate on the first object, and then due to the convolution theorem there will be a multiplication. So the Fourier transform of the first object multiplied with the Fourier transform of the second object. So this is what we have applied the convolution theorem in the second row. Now the Fourier transform of small object O at the coordinates at the space variables x comma y is written below, which is capital O, which is the spectrum of the small object O, capital O, at the coordinates at the Fourier coordinates f x comma fy. And on the right hand side we have replaced the complex Fourier transform of the complex conjugate of the object which was at coordinates minus x comma y by the Fourier transform by the spectrum conjugate, by the conjugate of the spectrum evaluated at the coordinates fx comma fy. And you know that we have O and its complex conjugate multiplying together, and that is why we can write the absolute square of O evaluated at the coordinates fx comma fy. So you see that here we have proved using the convolution theorem, that is the autocorrelation between the two functions is equal to the absolute square of the quantities of the absolute square of the spatial of the Fourier spectrum of the quantities. In other words, the Fourier transform of the autocorrelation function in space domain is equal to the power spectrum of the function. Here, rather than writing speaking about the power spectrum, it is more appropriate to write the energy spectrum. So here we can say that the Fourier transform of the autocorrelation function in space domain is equal to the energy spectrum of the function. Okay, now the question is then under what condition the autocorrelation will be equal to the convolution. So is there any condition that we can write that the autocorrelation of a function is the same as the convolution of the two functions? Let's analyze it. So we have here I am in the first integral giving you the definition of the autocorrelation of the functions, that is O at p comma q autocorrelated with the complex conjugate of O at p comma q is equal to the double integrations of the, and the integrands are O at zeta comma eta multiplied by O conjugate, that is the conjugate of O at the coordinates zeta minus p comma eta minus q, and the integration is with respect to zeta and eta coordinates. So this is the definition, and look at this definition, that this definition differs from the definition of the convolution in that this O conjugate is not the O conjugate, but it is simply O when we are talking about the definition of the convolution. And rather than writing zeta minus p in the convolution in definition of the integral, we have p minus zeta, and eta minus q will be replaced by q minus eta. Then the integral will becomes equal to the definition given for the convolution integral. Okay, now let's start with this definition of the autocorrelation function. Now in the second step on the right hand side, look at the integral that we have replaced the conjugate of O with simply O, because we are assuming that O is real. So if O is real, the conjugate of such an object has no meaning. That's why we have replaced the conjugate of O from the first integral into the second integral simply as O. Now look at the third integral. In the third integral we have reversed the coordinates, that is zeta minus p in the second coordinate has been replaced by p minus zeta, and eta minus q in the second integral has been replaced by q minus eta. because we are assuming that O, the object O, is even function. So if it is even, we can reverse the polarities of the functions. And then you know that this last integral, that is the third integral, is what is nothing but the convolution integral. So we can write this simply as O at the coordinates P and Q convolved with O at the coordinates P and Q. So on the left hand side we have the autocorrelation function, and on the right hand side we have the convolution between the same two functions. And what conditions we have used? The conditions that we have used is that over O function is real, and the second condition is that we have used is even. So if over function for which we are evaluating the convolution or the autocorrelation or the convolution, if the function is real and even, then of course the autocorrelation of those functions will be equal to the convolution of a functions. Okay, now you see that we have been using above the definitions, that is, if O at the coordinates PQ is real and even, then we can write, this is the definition that we have obtained, that is the autocorrelation between the two functions is equal to the convolution between the same functions. The conditions is that the O should be real and even. Now autocorrelation may be defined symbolically in the following two ways. You see that on the left hand side we have used O at P and Q autocorrelated with the conjugate of O at the coordinates P and Q. This is what we have been using, but you know that this is just a symbolic representation. It has nothing to do with the integral definitions that is given in the first integral over here. So in the first integral, whether we are using on the left hand side O conjugate or simply O, the integral definitions would not change. So in the integral we are always using as the conjugate of O in the second for the second object. So in the second, or simply we can write this definition that we have given on the left hand side, which we have been using, can be replaced simply by O as a function at P and Q autocorrelated with O at P and Q. So this is just the symbols that we can use to represent the autocorrelation. The integral that is associated with any of these two is the same. So don't change the integrals, the conjugate, complex conjugate in the integral with simply this one. This cannot be changed. So the autocorrelation, these are the two symbols that we can use in the autocorrelations, but its integral definition would remain the same. That is what we have stated. Okay, now the question is that how can we implement the autocorrelation in an optical setup? So the optical setup that I have shown, you can consider that one. The first object, I have shown the two pictures over there, the two objects in the transmission mode. One is represented by O at the coordinates Z, X and Y, and the other one at the coordinate O, and the other one same object, but this is the displaced copy of the object at the coordinates O at X minus capital X and Y minus capital I. So the second copy is a displaced version of the first copy. The two copies are separated by this distance S. The S is small, that is the field just after the first copy is the same as the field incident on the second copy, because the distance S is assumed to be small. So let's see what we have written on the right hand side of this. The original object O at X comma Y and its displaced copy O at X minus capital X, Y minus capital Y are shown in the figure. So you see that this capital X and capital Y can take all possible values at the object plane having the dimensions of the object O defined at X comma Y. So you know that what is the dimensions of the original object, the capital X in the second object, the capital X and capital Y in the second object can take any values such that the two copies should always be overlapped, or maybe a little bit larger values capital X capital Y can take such that the second object can move away such that there is no overlapping between the two objects. So our main objective is to calculate the area between the two functions, because the integral that we were talking about over here, you know that this integral means that we are always calculate the area between the two objects, that is O and its conjugated copy, and also the displaced version of that one. So in order to calculate the area under the two curves, under the two objects have to be displaced. When they are undisplaced, that is the second object has moved much away from in comparison with the first object, such that there is no overlapping, then we would say that no overlapping mean that the integral is equal to 0. Okay, now O, which define at xy, is illuminated by a normally incident unit amplitude plane wave from the left. So so we have shown these arrows over here, but these are actually the plane waves of normally incident on the first object O at coordinates xy, and these are the unit amplitude plane wave normally incident on the object. Now we want to calculate the fields over here. The field just before the object O at xy is equal to 1. There is also some constant phase vector due to the plane wave that we have dropped, because the constant phase vector on a plane wave would not make any difference. So we have dropped a constant factor with 1, but 1 indicates the amplitude of the plane wave. Now this 1 will be incident on the object O. So field just after the object O at the coordinates x and y will be equal to the same as O x comma y, because O multiplying with 1 will give you the same value. Now the field just before this O, which is a displaced copy of the original object O at x minus capital X comma y minus capital Y, the field just before this object will be equal to the original field incident on that one, because the field from the first object O will remain unchanged and will illuminate the second displaced version of the object, because in the above figure S is so small, that is the S over here, which is the separation between the two objects, original object and its displaced version, is so small that we can ignore the contribution of S. Okay, now the field just after the object O, which is at x minus capital X and y minus capital X, the field just after this displaced version will be equal to the field which was the incident on this one, which is O at x comma y and passing through this object, which is O at x minus capital X, y minus capital X. This field is collected by the lens which performs the optical integration at the detector P. The detector P, you see that we have also shown the detector P in the figure. So we shall evaluate the autocorrelation coefficient as a function of x comma y, that is given in terms of the integral. And you see that this is the same integral which is the autocorrelation integral, except that we have not used the complex conjugate of this quantity. It is because the object is real. So object is real, its displaced version, its displaced copy is also real. That's why we have not used the displaced copy. We have not used the conjugate on the second displaced copy. Now what we have to do is that we can take all possible values of capital X and capital Y from negative values to the positive values, covering the dimensions of the first object, and evaluating this integral. So putting the values of capital X, capital Y from negative values to all positive values, all possible values on the plane of the object, we shall calculate all possible values of the coefficients for all possible values of x comma y, and we can put these values of autocorrelation coefficients in a blank image at the coordinates x comma y, and we can form an image which will be called as the autocorrelation image. Now if a second object is different from the first object, then we shall talk about the cross correlation. Then the signal will not be autocorrelation but cross correlation. So you see that this integral will actually also evaluate the similarity between the two functions, that is the object O at x comma y and its displaced version O at x minus capital X and y minus capital I. So when capital X and capital Y are equal to 0, then both objects will be the same and the integral will give you the maximum value. So A coefficient will have the maximum value, which means that the two objects are the same, are much similar to each other. So this integral will give you, that is the A coefficients, autocorrelation coefficients will determine the similarity between the two, between the original function and its displaced copy. So from the image of the A coefficient, when the peak, where the peak would occur, that peak would indicate that the position when the two copies are exactly identical to each other, giving the maximum value of the area under the curve. And A coefficient of x comma y is the autocorrelation coefficient, and I have also talked about the cross correlation between them. Okay, now with this, this is the end of slide number 22, slide number 32.